All right, guys, I'm gonna go through this warm up with you guys. So we're gonna be optimizing trig functions today, and so you guys know from our last unit, so that meant finding a derivative, setting to zero, and solving. So that means we're gonna have to be solving equations that involve trig ratios in them. And I know everybody here did all the prerequisite work and practiced up, so I know you guys are already good at all this stuff. But I thought just as a safety that we would go through some strategies together to use when we do our examples today. First thing I want to mention, so you guys now after grade 12 functions can work in degrees or radians. And if you're wondering, should I give my answers in degrees or radians? It really depends on the context of the question. So I'm just going to add a little note up here. You guys should just make sure, hey, am I looking for degrees or radians? Because that will tell you whether you should have your calculator in degree mode or radians mode. And again, the context will usually tell you what to do. For example, in this first equation we're going to solve, we're looking for solutions between 0 and pi, including 0 and pi. So that means we're going to be working in radians. So if your calculator wasn't in radians yet, maybe you want to make sure it's in radians. So how do we solve an equation like this? So I've got three equations because there's kind of three strategies. In A, there's really nothing preventing us from just getting cosine by itself, just like we were back in grade 9 math, kind of getting an x by itself. So let's just rearrange this equation for cosine. So that'd be 2 cos theta equals -1. And you can actually just get cosine theta by itself. Cosine theta equals -1/2. And then there's two ways we could go from here. You guys all have your unit circles tucked away from last week. Why don't we take a second? Once you get out those unit circles, see if you can find the angle that has a cosine value of -1/2. I'll have a sip of coffee while you guys do that. All right, we're looking for a solution or two maybe between 0 and pi radians. The cosine is -1/2. Anybody spy the angle that has a cosine ratio -1/2? There is one. It's kind of staring you right in the face there. Maybe I'll give you guys a bit of a prompt. Maybe you guys can tuck this in. I'm going to tuck this in the top left of my note here. One of the big ideas we talked about, and you guys just have to have this in your back pocket, that on the unit circle, points on the unit circle correspond to the cosine of the angle and the sine of the angle. You guys remember talking about that? Well, we talked about it a few days ago, literally. Can you guys find a point on the unit circle that has an x value of -1/2? Jacob, you got one? 2 pi over 3. We figured it out. So theta is equal to 2 pi over 3 radians. And I'll just add in brackets. We got that from the unit circle. But sometimes, not every value has an angle on the unit circle, like plotted for you on your sheet. It only has some special angles. So you could use your calculator as well. So can you guys humor me And let's whip out our calculators. And can you guys make use of your inverse cosine function? Can you just pop in the cosine inverse of negative 1 over 2? I will do it as well. Make sure I'm in rad mode. Shift cosine negative 0.5. So I got about 2.09. Did you guys get 2.09? We got different answers. But no, what's 2 pi divided by 3? You guys can just hammer that out. Let's just check. 2 times pi divided by 3. 2.09? All right. So you guys just keep that in mind as you're doing practice. If it's a special value, you might see the answer as exact. And it's good to keep them as exact. But you can always just use your calculator. And I might just add in brackets here. We got the same answer using our calculator. Some of your calculators might even take that and give you exactly 2 pi over 3. I don't know. Mine doesn't. Okay, so strategy 1. You can just isolate the ratio and then use the unit circle or use your calculator. And between 0 and pi, that's the only solution. Let's look at part B. Oh my gosh, there's a sine and a cosine. So I can't get one by itself and use method A. What am I to do? Anybody have any ideas, actually? It involves one of the identities you guys learned in grade 11. Let me show you. So the idea is we can turn this into a situation like part A. Pretty easy, actually. If you do a bit of rearranging, if 0 is sine theta minus cos theta, that means that sine theta is actually equal to cos theta. And just actually, for interest's sake, I might just pause there. You guys know that cosine theta corresponds to x values on the unit circle, and sine theta corresponds to y values on the unit circle. Can you guys find a couple of angles where the x value in the unit circle is the same as the y value in the unit circle? Anybody find one or two even? Jacob, you got one or two? So Jacob has just solved this equation, at least between 0 and 2 pi. But that doesn't always work, but that's great. We can make use of the unit circle too. We now know what to expect. But I'll show you guys a strategy that kind of works all the time, even if we don't get a special scenario like this. We can turn this into an equation that has one trig ratio by dividing both sides by the cosine of theta. Because everybody knows from grade 11, sine theta over cos theta, that's equivalent to tan theta. And then cosine theta divided by itself is equal to 1. All right, and at this point, we can use our calculators. Let's just use our calculators here. Arguably, tan theta equals 1 is one of the theta is one of your special angles you guys learned in grade 11. But let's just use our calculator to get a decimal equivalent here. So we're going to do tan inverse of 1. I'm just going to give you something that works all the time. So tan inverse of 1, it's going to spit out an angle for you. I'm going to do it too. Second tan of 1 equals. You guys get about 0.79? Exactly, this is pi over 4. I'm just curious, does anyone's calculators actually spit out exactly pi over 4? I see some nods. You're lucky. Yours says Maya. Lucky you. Mine does not. Or maybe it does, and I just don't know how to actually make it look that way. Anyway, let's continue. So that is one possible answer. Note that we're looking for possible solutions from 0 to 2 pi. So how do we find another one? So everybody remembers back in grade 11, remember the cast rule? Tan is positive in 2 quadrants. We found one possible solution in one of those quadrants. Since I have space here, I'm just going to make a little visual. Which one did we just find? We found pi over 4. Pi over 4 is located in quadrant 1. We found pi over 4. And then I might actually just, label my cast rule CAST, something like that. Where's the other possible solution? Well, it's the other quadrant where tan is positive. It's the bottom left one down here. It will have the same related acute angle. It'll also make an angle of pi over 4 with the x-axis. And now we can get our second solution using the cast rule. So using the cast rule, theta equals, what is that angle? That angle that is pi over 4 past the negative x-axis, and we all know the negative x-axis is pi radians. The second solution is pi plus pi over 4, which is like 4 pi over 4 plus pi over 4, 5 pi over 4. We get the exact same two answers that Jacob said earlier using our calculator or using our knowledge of special triangles, and then using the cast rule. So a second strategy, maybe sometimes you can massage your equation to maybe just have tan or just have one ratio, and then you go about your business. So 2 examples down. Anything you guys want to chat about? All right. Let's look at our third example. This is going to be relevant to us today because we're going to use this method in our next example. So 0 equals 2 times cosine squared theta plus cos theta minus 1. Note that in this question, for whatever reason, we're looking for an angle in degrees. We're looking for a possible solution between 0 and 180 degrees. So keep that in mind for later. But how do we do this one? Because I can't rearrange that and get a cosine theta all by itself. I got a cos squared theta. Some of you guys might try, but you can't do it. Nor can I use any trick like B to just get one single ratio. So what do we do? You guys probably solved some of these last semester with Mr. Colosimo. Hopefully you can all recognize that's actually kind of like a quadratic equation. Just instead of x, we have cosine. So we can actually kind of turn it into a quadratic equation. Doing a little change of variables. I might do this. Let's, instead of having cos theta in there, I don't like the looks of that. Let's let cos theta equal your favorite letter of the alphabet. Let's use u. If I replace everywhere I see a cosine theta with u, I get this. I get 0 equals 2 times u squared plus, well, cosine theta is equal to u minus 1. Okay, that's just a quadratic equation. You guys solved literally like 59 of those back in grade 10. So we can do that here. You could use the quadratic formula, but this one can be factored. So I'm going to factor this one with you guys. You factored probably like 64 complex trinomials back in grade 10. So we should be practiced up. So we're looking for numbers that, in this case, add to 1, the middle term, and multiply to the product of the outside terms. 2 times minus 1 is minus 2. Those two numbers are negative 1 and positive 2, I think. So we're going to use some decomposition here. So 2u squared plus 2u minus 1u minus 1. In physics mode, I wrote the Greek letter mu. Excuse me. There we go. And then we can group factor to finish this off. If you have a different preferred way of factoring complex trinomials, you can do it that way. I'm not your dad. Do what you want. Oh, and excuse me. I can factor out a 2 from those first two terms, can I? 2u times u plus 1. I can factor a negative 1 from the last two terms. I'm left with u plus 1. Hey, things are looking good. 0 equals 2u minus 1 times u plus 1. However you like to factor, factoring is a reasonable expectation for you guys in this course. We now have it to a point where now we actually can figure out, well, what is u equal to and what is cosine is equal to? So from this first bracket, what makes 2u minus 1 equal to 0? I got lots of space, so I'm just going to use it. So what makes 2u equal to 1? What happens when u is equal to 1/2? But if you guys recall, we said that u is equal to cosine theta. And we're in degree mode in this question, so make sure that you're in degree mode. Can you guys use your calculators? What does your calculator spit out for the angle that has a cosine of 1/2? Remember, we're only looking for solutions between 0 and 180 right now. Cosine is negative between 90 and 180, so we should just get one value, an acute value. Should work out nice, right? It's either 60 or 30. I forget which one. It's 60? All right, save me some work. Theta equals 60 degrees. So I'll put a box around that. That's one possible answer. But also, what makes u plus 1 equal to 0? We could get another solution from here. So that means that u is equal to negative 1. So that means cosine theta is equal to negative 1. So is there a value between 0 and 180 that gives a cosine of negative 1? Unit circle calculators will give you the same thing here. It's 180, right? Of course it is. Yeah, I'm still in radians mode. So it popped out 3.14 for me, pi radians. We're working in degrees. You guys get 180 degrees as well? All right. Now, if you guys had used the quadratic formula, and maybe you did where you are, you would have got u equals 0.5, and we would have got the same thing. You would have got u equals -1, and you would have got the same thing. So these are the three strategies we have to have in the toolbox for the stuff we're doing. Anything you guys want to chat about? All right, hang on to your butts. So now we're gonna do some optimization problems. I know how much you guys love these. Two, in my opinion, actually pretty useful ones. So the first one has to do with an eaves trough. You guys know what an eaves trough is? Anybody's parents make them clean these out? Get all the old mucky leaves out of them. Make sure the water can all flow through in a heavy rain. So these all line your roofs at home. And these eaves troughs are basically made of pieces of sheet metal. So like I know some of these have fancier designs, but what we're gonna just do in this simplified example is imagine just like a rectangular piece of metal, and we're gonna fold it in such a way that it kind of makes an eaves trough. So we're saying this 10 centimeter part is going to go against the wall, and that's fixed. It's 10 centimeters. And then we're going to make another fold 6 centimeters from the left-hand side. And depending on how we fold that piece of sheet metal, a different angle, it's going to make different kind of shapes of eaves troughs, right? Like some will be very, very shallow, and like there won't be a lot of depth to the water that can flow through it, but it can be wide. And some of these, and maybe we won't go past 90 degrees, but you can also make this a rectangular eaves trough. How should we make it? Well, hopefully you guys would agree. You want your eaves troughs to have a really big cross-sectional area, so lots of water can flow through. Because if the water starts to spill over top of it, could get into your house, could damage your attic, get into the other floors. It's just not a good thing. You want the water to flow through the eaves troughs, and then it goes down, whatever you call the thing on the corner of your house, downspout perhaps. I'm not that kind of guy that knows all this stuff. And then it flows out into the street, into the gutters, and everybody's safe and warm in their houses. So that's the premise of this question. We want to maximize the area of this, the cross-sectional area of this eaves trough. You guys get the idea in principle? All right, so our step one, we need to get an expression for that cross-sectional area, which is a trapezoid. And I know you guys all remember area of a trapezoid from your grade 9 math course, right? I'm just kidding. I'm going to work it through with you guys here. All right, I'm going to make Miss Plattner proud, and I'm going to manage my space really, really well in this example here. I'm going to do a bit of a development in the top right here. I think you guys should do this with me. I'm going to kind of draw a little bit of a bigger diagram of my eaves trough, something like this. And the cross-sectional area would be, I'm just making a dashed line from the tippy top of this 6 centimeter line. The cross-sectional area is going to be the area of this trapezoid. What do we know about this trapezoid? We know that the bottom side is 4 centimeters. Go away, news. I said go away. Windows 11, go away. We know the bottom side is 4 centimeters, but actually right now, that's about all we know in terms of this trapezoid. To get the area of a trapezoid, we need the bottom side, we need the top side, and we need the height of this trapezoid. None of those things are actually given to us. So how can we get them? I'm going to show you guys. So I'm going to add in a little dashed line here, and I'm going to pop in our angle theta. And I'm going to just kind of complete a little right angle triangle on the bottom left-hand side, just like so. Maybe the last thing I'll put on here, we do know that the hypotenuse of that right angle triangle I just drew is 6 centimeters. What we need to do is get an expression in terms of theta for the other two sides of that right angle triangle, because then we'll know the height of our trapezoid, and then we'll actually be able to get an expression for the top. So maybe I'll just do, let's just do the teeniest of tiny little, you know what, I'm just going to go down here. A little grade 10 SOHCAHTOA review for you guys. So you guys know that the cosine of an angle is the adjacent side over the hypotenuse side. So how can we get the adjacent side? Go away, news. If anyone knows any Windows 11 people that work on this, tell them to make that stuff stop popping up. So we can get an expression for the adjacent side. The adjacent is just the hypotenuse times cosine theta. Which means an expression for our little bottom side right here. Well, the hypotenuse is 6 times the cosine of theta. So hopefully after that little team talk, you're okay with that. That bottom side in that right angle triangle is 6 cosine theta. Maybe you see where this is going, but just for completeness sake, I'll do the same thing for sine. Sine theta is opposite over hypotenuse. So if you want the opposite in a right angle triangle, people who've taken physics might know this shortcut already. Just do the hypotenuse times sine theta, which means this vertical side would be 6 times sine theta. Yay us, we have the height. Oh my gosh. Windows 11 news is just popping up everywhere. We have the bottom side of our trapezoid. We have the height of our trapezoid. The last thing we need is the length of the top side. And we actually have that, guys, because this part of the top will be 4. The remaining part is 6 cosine theta. So an expression for the top side is 4 plus 6 times cosine theta. We haven't even started the problem yet. This is just grade 9 math stuff along with SOHCAHTOA. It's manageable. You guys have the tools. So let's get started. We're maximizing the cross-sectional area. The area of a trapezoid, and I joked, I don't expect you guys to know the area of a trapezoid. It's kind of obscure. But what you do is you average the top and bottom parallel sides, and then you multiply by the height of the trapezoid. And maybe you even do remember that from grade 9. We actually now have expressions for all those things. We have enough to get an area function in terms of just the angle theta. Here's what it looks like. Let's dive in here. So let's use A as the top side. The top side was 4 plus 6 times the cosine of theta. And I think I can afford to zoom in a little bit now. The bottom side of that trapezoid is 4. All divided by 2. And the height of our trapezoid was 6 sine theta. The only variable in that expression is theta, which means we can go about our usual process of find the derivative, set to 0, and solve. No problem. But maybe, just maybe, we should clean this up a little bit to make it easier to find the derivative of. So let's do that. Maybe I'll do this. Would you guys agree that 6 divided by 2 is just 3? Can I just do that? 6 divided by 2 is 3, right? Pretend we're on Barney the dinosaur here. And then I can just collect like terms inside the bracket. 4 plus 4 is 8, more Barney. So 8 plus 6 times cosine theta times 3 sine theta. That's an expression for our area, which is fine. But maybe before we take the derivative, we can just distribute the 3 sine theta in there. 24 times sine theta plus 18 times sine theta cosine theta. Look at us. We now have an expression for the area of our trapezoid, and it's just in terms of theta. Moreover, it's kind of in a form. I think it's reasonable that you guys could find this derivative. Can you guys give that a go? I won't leave you hanging. I'll come along for the ride too. But can you guys at least start? Try to find that derivative. A prime of theta. It's not so bad. 24 sine theta, it's not bad to do. I hate Windows 11. And then the second part has a sine theta, cos theta. It's the product rule. So just give it a go. I'll help you do the simplifying. First step would be great. All right, here I come along for the ride. The derivative of 24 sine theta is 24 cosine theta. No problem. Plus, the derivative of 18 sine theta is 18 cosine theta, and we leave the second guy alone. Plus, we'll leave 18 sine theta alone and take the derivative of cosine, which is minus sine theta. So at the very least, I think that's reasonable. Windows 11. For you guys, so did you guys get the same thing? Something similar? All right. We have to set this equal to 0 and solve it. There's going to be a few steps, all manageable. Let me walk you through what we can do here. Let's maybe clean things up a little bit. So I see cosine theta times cosine theta. Let's write that as cosine squared theta. So we have 24 cos theta plus 18 times cosine squared theta. And then I have 18 times sine theta times minus sine theta. Maybe I can clean that up. Minus 18 sine squared theta. And we're setting that to 0, so I might do that right now. Pop a 0 on the left-hand side. All right, maybe we can use the strategy from the front now. I see some cosine squares, so maybe we use the strategy we did in part C. Except I've also got a sine squared as well, right? What do I do? Well, luckily, Mr. C taught you guys your trig identities, and you guys know that we can always take sine squared theta or cos squared theta and write that in terms of cos squared theta or sine squared theta, like vice versa. We can actually take sine squared theta and turn it into 1 minus cos squared theta using everybody's favorite identity, the Pythagorean identity, right? So 24 cos theta plus 18 times cos squared theta minus 18, and we can replace sine squared theta with what it's equal to. Sine squared theta is equal to 1 minus cosine squared theta. That's a little trick. Remember when Mr. C made you guys prove a whole bunch of identities? Building you up to this moment, we can replace sine squared theta with 1 minus cos squared theta. I do have a little bit of space here. So when you guys are going back and studying, maybe I'm just going to tuck in, reuse the Pythagorean identity at that spot there. You know what, guys? You honestly got it from here. You don't need me. Everything's in terms of cosine theta. We maybe should clean this up a little bit, but then we can use our part C strategy. Replace cos theta with the variable. Use a quadratic formula. Everybody can do it. I believe in you. But let me help you along the way here. How much room do I have left? Hopefully I won't make Miss Platinum mad at me. I got lots of room. We're doing good. So let's take a couple steps here to put this into a form where you guys can use the quadratic formula. So we have 18 cos squared theta minus 18, and minus 18 times minus cos squared theta is plus 18 cos squared theta. And then there's a couple of like terms we can group together there. And I might put the squareds first. So that's 36 cosquared theta plus 24 cos theta minus 18. And of course, we just popped up. Would you guys agree? It now is just like part C, right? It's exactly like part C. Do you want to factor that? I don't know. Maybe you can try. If you just like using the quadratic formula, you can do that too. Let me give you a few helpful tips though to make the numbers manageable. 36, 24, 18. Those can all be divided by 6 just to make the numbers smaller and more manageable. That's not necessary. That's just some tech that'll help you guys out. So 6 cosine squared theta plus 4 cos theta minus 3. At this point, for people that like factoring, you might realize this one actually cannot be factored over the integers. So we do have to use the quadratic formula. And then we're just going to use the same strategy as before. I'm going to replace cos theta with u. Not your dad, though. You can use x, you can use n. I wouldn't use an s because my s's look like 5s, so probably a bad choice, but u would be fine. So 0 equals 6u squared plus 4u minus 3. All right, can you guys use the quadratic formula to get 2 possible values for u? And then we'll wrap things up. You guys are doing great. All right, so we have 4 squared minus 4 times 6 times minus 3 all over 2a, which is 12. So what's that? 16 plus 72, so that's 88. And we're going to get a couple of decimal answers for you. We'll see if both of them are possible or if only if one of them is possible. Hopefully one of them is possible. And just out of habit, when I'm finding angles, I like to keep these decimals to 4 decimal values just to make sure I'm super accurate. Do this with you guys since I made you guys suffer. Let's do it as well. 4 plus 8 divided by 12. All right, so I got, I'll just maybe say U1 equals 0.4484. Did you guys get that too? No? How did I do? 0.4484? All right, our calculators can spit out the angle that is equal to. So remember that's equal to cosine theta. And what angle has a cosine value of 0.4484? Hey, maybe we should discuss. Do you guys think this question would radians be most appropriate for this question or degrees? Like if I was telling the guy in the shop class, hey, can you make sure to fold these up at a certain angle? You think they would appreciate degrees or radians? Probably degrees, yeah, unless you want to get punched in the face. Probably degrees. So I'm going to have my answer in degrees. And what do we get? 0.4484. I'm still in radians mode. That should be punched in the face. Mode, degrees, shift, cosine 0.4484. About 63.4. About 63.4. Okay, so we get 63.4 degrees. But maybe there's another optimal angle to fold our eaves trough. Let's check. So what do we get using subtraction with the quadratic formula? So negative 4 minus the root of 88 divided by 12. to 4 decimal places, negative 1.1151 if we round accurately. What do you guys get when you try finding this angle on your calculators? You get a math error, right? Of course, everybody knew that was coming. If we look at our unit circle, are there any points in the unit circle that have an x value beyond 1 or negative 1? No. It's impossible for cosine to be more than negative 1. And you guys know, too, from the graph of cosine, it goes as high as 1 and it goes as low as negative 1. So we don't actually get any solutions from that second bit. So we can just write no solutions. And look at us, guys. So now you guys can go into the eaves trough business and have you guys can advertise our eaves troughs are perfectly optimized for the cross-sectional area to allow the most rainwater through your eaves troughs to keep your house safe. Let's just wrap this one up with a concluding statement. You know what? It was a lot of work, but we're not in grade 11 workplace right now. We're in calculus. If you think that's bad, wait till first year calculus. Fold the eaves trough at 63.4, and I'm too lazy to find the degree symbol in Cami here, so I'm just going to actually just type out degrees. There you go. I would argue every step, there were a lot of steps for sure, but every step, in my opinion, is manageable. It's grade 9 math with area of a trapezoid. It's grade 10 math with SOHCAHTOA. It's it's calculus. We're finding the derivative of a trig function, and it's solving that equation. But you guys solved trig equations last semester with Mr. Colosimo. Every step is manageable. I believe in this, and this is a worthwhile question. People have to think about these kind of things, right? Okay, so before we move on to our second example and final one, any specific individual step that you guys want to chat about before we go on? All right, then. I've got another, I think, worthwhile optimization question for you. Hey, Cole, you know what? If you find this stuff challenging, maybe you want to lock in and just pay attention. Okay? Just a strategy might be valuable. So many of you guys will be moving into a new spot next year, possibly. Maybe a dingy little house with 7 bedrooms. You got to get your what do you call those beds that fold into a couch, but they're also beds, but they're also couches? Without couch, there's a kind of I forget the name. But you're gonna have to move some stuff around some tight corners. And you know what? You guys can be the smart one. You know, if something is literally impossible to fit around a corner, you might as well not even try, right? Without damaging the stuff. Like if you have a box spring that's like 8 feet long, and the smallest tightest spot going around the corner is only 5 feet. Like you might as well not even try. It's just not happening. So that's kind of the idea behind this question. Also, if you're a Friends fan, this was a funny episode of Friends where they were trying to get. I forget it might have been a couch, but we're doing a box spring. So a box spring, you guys know what a box spring is? It's like what you put your mattress on. But unlike a mattress, you can't like fold and bend the box spring unless you want to like glue it back together. So we have to fit a box spring 2 meters long around a tight corner in a hallway. So the idea is we have to figure out what the absolute tightest this corner gets. As we rotate our mattress and this angle changes, the distance, this diagonal distance around the hallway is going to get smaller and smaller and smaller until we reach a certain point and we're leveling it back out, and it becomes wider again. We need to find how small does this diagonal length get. If that diagonal length is the smallest it gets, is allows us to fit our 2 meter box spring, then we're good. We're good to go. If not, we might as well not even try. So here we go. We're going to find the minimum diagonal length around this corner. And I'm going to make Miss Plattner very proud again and manage my space. I've got a little aside for you guys, a little SOHCAHTOA aside that we'll do just to make the setup easier. And you know what? Maybe I'll do this first. To get an expression for this length, would you guys agree that this length is made up of kind of like this diagonal length, I'll call that L1, and that diagonal length, L2? Hopefully you guys would agree with that. So we're trying to minimize this total length with this, which is the length of that first diagonal from the upper hallway that's 1.5 meters wide, in that bottom hallway, which is 1 meter wide, L1 plus L2. But we need to get expressions for those lengths in terms of theta so we can use our calculus techniques. So I'm going to just do this off to the aside. I think we have lots of space with this one. I'm going to pretend I'm teaching my grade 10 applieds here. We've got our hypotenuse. We've got our, I'll call theta down here. We've got our adjacent side. We've got our opposite side. And in each of these two lengths, maybe I'll drop a little dashed line there, L1 and L2. In each of those cases, they are the lengths of two triangles. In this top triangle, we're looking for the hypotenuse. We know the opposite side is 1.5 meters. I might tuck that into my diagram. 1.5 meters right there. And on the bottom side, I don't think I'll need to rewrite that. The bottom side, the adjacent side of that bottom triangle is 1 meter. I need to get expressions for the hypotenuse. So let's just add this down here. So you guys know sine theta is equal to opposite over hypotenuse. I guess I'm using all caps for this question, which means if you guys wanted to get the hypotenuse by itself, just rearranging that, the hypotenuse is equal to the opposite side divided by sine theta. Just rearranging sine as opposite over hypotenuse. And in the same way, cosine of theta is equal to adjacent divided by hypotenuse. So if you have the adjacent side, you could get the hypotenuse by doing adjacent divided by cosine theta. And we're going to just do that right now. A little bit of an easier setup than the previous one. We now have an expression for that minimum diagonal length, L in terms of theta. That top length, since 1.5 is the opposite side, I can get an expression for L1 by just doing 1.5 divided by the sine of angle theta. And I can get an expression for L2 by doing the adjacent side, which is 1, divided by the cosine of theta. Little bit of grade 10 SOHCAHTOA. And now we have an expression that we can find the derivative of, set to 0, and solve. You guys okay with the setup there? A little bit of SOHCAHTOA action. All right. I've told you guys before that when you guys all become math teachers, never improvise because it always fails. So guess what we're going to do? We're going to improvise. I just had some inspiration. 1 over sine theta. You guys know that's equal to cosecant theta. Cosecant theta, CSD theta. And cosine theta, you guys know that's equal to 1 over cosine theta is equal to the secant of theta. Did you guys not just find these derivatives on Friday? We did that in our notes, right? Yeah. So do you guys just want to look up those derivatives and let's find the derivative of this length expression? You can just look these up in your notes. No product rule, quotient rule. And literally, I need you to look them up because I don't know them by heart. So I need you to look them up. You guys can watch my video on this from a previous year and decide if this method's better or not. All right. You know what? I will look this up with you guys. Which lesson was this? Other trig derivatives. All right. Cosecant theta. What was that derivative? It was like tan theta cosecant theta or something, right? Derivative of cosecant minus cotangent cosecant. How could I have forgotten that? It's so clear. All right. So the derivative of cosecant x. So this will be negative 1.5 cotangent theta cosecant theta. I have made a horrible mistake. No, I haven't. We're going to be fine. And then the derivative of secant theta, just looking it up here, we did that down here. Tan theta times secant theta plus tan theta times secant theta. That look okay to you guys? All right. We have to set this equal to 0 and solve it. We didn't do anything with our 3 strategies for solving equations that involve a mixture of all these reciprocal ratios. What we did do is we solved one that has, in part B, that has sine and cosine in it. Let's replace cotangent, cosecant, tan, and secant with what they're equal to. So remember, cotangent is cosine theta over sine theta. Cosecant theta is 1 over sine theta. Tan theta is sine theta, I'll use brackets too, I guess, sine theta over cosine theta. And secant theta is 1 over cosine theta. How is this making things any easier? Guys, just have a little bit of faith. Let's clean it up a little bit. So from the first one, we get minus 1.5 cosine theta over sine squared theta. The second one is plus sine theta over cosine squared theta. And maybe you see where this is going. In part B, we had sines, we had cosines, but we massaged the equation to get it just in terms of tangent. So check this out. We have lots of room. I'm going to move that first bit to the left-hand side. It becomes positive 1.5 cos theta over sine squared theta equals sine theta over cos squared theta. And guys, look, if you do a little crisscross applesauce here, multiply up the cos squared theta times cosine theta, multiply up the sine squared theta times sine theta. Check this out. We get 1.5 times the cosine of cubed theta equals sine cubed theta. Remember what we did in part B? Sine divided by cosine is tan. We can do that here. If we divide everything by cosine cubed, we get this. We get that 1.5 is equal to tan cubed of theta, which means tan theta is just the cubed root of 1.5. They're great, guys. So we can just wrap that up. What's the cubed root of 1.5? And then what angle does that give us? Again, maybe we should be in degree mode here. All right, I'll do it too. All right, you guys tell me if you got this. I got about 48.9. You guys got about 40.9? That means is this corner is the absolute tightest it can be when the angle that our box spring makes was 48.9. 48.9 is the absolute tightest. And then after that, when you keep rotating, it gets easier and easier and easier. So how long is this diagonal when the angle is 48.9 degrees? If it's more than 2 meters, our box spring can fit. So that's the last thing you guys have to do. Can you slam in 48.9 degrees in here? And let's see what we get for the length. Hopefully, it's more than 2. I'm sad to say, I don't think, even though Miss Plattner would say, nice solution, Andrew, she probably would say that I did not manage my space that well. I'm going to tuck this up in here. So what is our length when you plug in 48.9 degrees? So it'd be 1 divided by the cosine of 48.9 plus 1.5 divided by the sine of 48.9. Did you guys get about 3.5? About 3.5. That's good. 3.5 is a lot more than 2, which looks like we're going to comfortably get our box spring around the corner. So I might wrap this up, just squeeze in a little concluding statement here. Since last time I checked, 2 was less than 3.5, the box spring will fit around the corner. Around the corner. Not only did we solve some complex, but I think useful optimization problems, we also practiced our fine motor skills. But I think that went well. You guys did really good. If you're interested, you can look at the video I have posted for another way to go about finding this derivative. It involves negative exponents with sine and cosine, which arguably some of you guys might not find easier, but maybe some of you guys do. But those are kind of the two types of problems that I would expect you guys to be able to do. Anything about this one you guys want to chat about? Everything manageable. Grade 10 trigonometry, reciprocal ratios, derivatives we've done already. I believe in you guys. All right. I actually have, for practice today, I'm going to stop.